Friction that are given in times
Urination
you don't use it because MG is now involved for saying charge. So that's all about force friction. Yeah. And there's also friction, right? It's hard to explain. It's like it's like you solve the normal force based on the y-axis, and then you solve the force forces.
Spring stretch by 10 centimeters.
I know by 10 centimeters, but what minus what? What the x minus
That's too close.
Since,
x. By 10 centimeters, that's what?
yeah, that's the stretch.
Okay.
So, yeah, what we do, we had to figure out what the stretch
Okay,
was.
you guys ready?
So we don't have to, okay.
One more second. Wait, where? Why do you have centimeters over centimeters?
I don't know.
Oh.
I can't instance was high or no. I got a big
Well, yeah, because like this, if I have my units, it'd be easy, but this is new, so he doesn't cancel out meters.
That's not what this is.
Samantha.
I think so. I
Nope, can we do this now?
Yeah.
All right.
I understood it, 'cause I was like,
By the way,
there'd be a force
I'm
this way,
thinking
but
that
since it's constant-
it's probably easiest just to think of to remember the magnitude of the spring force. It's just K times the length stretch. This is length stretch. Spring force, and then you don't have to, and then so the minus sign we had, that just gave me the direction, okay? This way you don't confuse yourself with having too many negative signs. Okay, you just know I have to oppose the stretch in the spring. Okay, So let's go ahead and draw a free body diagram for this. What are the forces?
We have spring forces.
Spring force.
Opposing friction force.
We have a friction force.
Normal force going up, and
You have a normal force going upwards.
then mg going down.
Down.
mg going downwards. Okay, so let's go ahead and let's just do sum of forces in the y direction. I'm going to introduce y and x like this. What's the sum of forces in the y direction?
0. Well,
0, yeah,
normal
because it's not accelerating through the floor.
force.
Equal.
Normal force minus mg.
Make all the normal force points in the up direction, and then mg is in the negative y direction. And so I get that the normal force is equal to what?
mg.
mg. All right, good. That's what I get from this equation. How about sum of forces in the x direction?
Friction force.
What's it equal to, first of
Oh,
all?
0.
0, why?
It's not
There's no
accelerating.
acceleration.
Yeah, that's right. It's moving at a constant speed. So that means it's not accelerating, or constant velocity, so it's not accelerating. So 0. And that would be equal to the spring force minus the friction force, right? What is the spring force? So we can say the spring force is equal to the friction force, right?
Yeah.
So spring force, the magnitude of it would be kd, right? K times the length that it's stretched. It would be K times V. V is equal to length stretched. And what's the friction force?
Normal force times
KN.
the
Normal force times mu K. And what's the normal force?
mg.
All right, so if I want to solve for K, right, what should I do? So I have this is equal to that.
Divide the D.
This divides the D. So I get K is equal to mv mu over D. Then I plug in numbers. So that's 10 kilograms times 9.8 meters per second squared times 0.4 divided by 10 centimeters. I want to put that into meters, so what's 10
Point one.
centimeters? 0.1 meters. Okay, and when I do that, what do you get?
390.
Yeah, 390.
190 newtons per meter.
92.
All right, and that means that this spring, in order to stretch it 1 meter, I'd have to exert 392 newtons. That's kind of what the spring constant means. That makes sense to you guys? You want to do another one? Now this one will be slightly different. We talked about the pulling of the spring and also pulling here of this on the spring, right? Actually, the spring constant applies whether you pull or push a spring away from its equilibrium point. So if this is my equilibrium point here, I'll get the same spring constant if I push it upwards, you know, from where it's happy to be at equilibrium. So let's say I have a block and I have a spring attached to the wall. Okay. And this is free to move. So I put little wheels on there indicating it's free to move. Except for the spring holding it. Let's say that the spring constant of the spring is 1,000 newtons per meter. And let's say this is a 100 kilogram block. see if I can come up with this problem. So, what I want to do is I want to say, okay, first of all, let me push this, let me push on this block. So, spring is compressed. This is an easy one. 20 centimeters. Okay, and then I let go. And then let go. What is the acceleration of the block? I'll give you 2 minutes to do that one, okay? This throws just a little twist in it of its pushing, but remember it's the same spring constant. It just opposes the whatever distance you are from equilibrium. Get it? All right. I think that was 2 minutes, right? 2 seconds. I'm just trying to estimate time. All right, that's been 2 minutes. Okay, so for this one, what I've done is I've compressed the spring a little bit. And if I were to draw a free body diagram on this box, for this box, I would see that the spring force points this way, pushing it away from the wall. And then I had to, that's the only force on it, right? In the X direction. You also have normal force and gravity, but I don't really have to worry about those in this problem, do I? Because I'm only looking at acceleration in the X direction. So if this is the force in the X direction, I can say that the spring force, which is force of spring, is equal to ma, right? In the X direction. And this would be k times the distance that it was compressed, which was 0.2 meters, is equal to ma. So if plugging in, solving for a, I would get that a is equal to k times d, which I already put in numbers, over m. This isn't a meter, so don't get confused. And so plugging in numbers, I'd get 1,000 newtons per meter, 0.2 meters over 100 kilograms. And so this would be 200 up here divided by 100. So that's 2 meters per second squared. Did everyone get it?
Yeah.
Now, you can see that if I push on something to compress the spring, I have to do work, don't I? Because not only am I exerting force, I have to move it. So I'm actually doing work if I want to compress a spring. And then if I let go of the spring, you can imagine that this thing would fly out. And it turns out that if I do work to compress the spring and then let it go, I get the same amount of energy, or after I let it go, I get kinetic energy of what was released equal to the amount of work I did to compress this spring. This spring is what we call, is another example of what we call the conservative force. The energy is conserved in it when I compress it. And we can talk about the energy of compression of the spring. And I'll just write this as the last thing I want to do today. So this is energy in a spring. So let me just, I'll keep this drawing there. Put K here. So let's say I start out with some initial length like this, and this spring's not compressed at all. It's at its equilibrium position. So I'm going to call this X naught. So this is initially. And then let's say that I slowly compress it so that at the end of everything, I'm basically keeping this block at rest the whole time. So this length now is X. In order to compress the spring, I have, and not accelerate it, keep it moving at a very slow, constant speed, I have to exert a force that's equal to that Hooke's law force at every point. So if I start here and I compress it, I have to keep exerting a bigger and bigger force to keep it, to compress it more. The force that I'm beginning with that I'd have to exert would be 0, because this thing's not it doesn't really require any force at this point because the spring's at its equilibrium point. So I don't have to exert anything when I first start pushing this very, very slowly. Over here I have to exert a force K times the X minus X naught, right? Or K times this distance. I'm going to call this D, okay? I have to exert a force KD at this point. Here, since it's at its equilibrium point, I don't have to exert any force to begin just barely moving it. Here, in order to keep it moving I have to go and exert a force KD, right? So the average force that I would have to exert to compress the spring at distance D would be KD plus 0 divided by 2. Initial force plus final force divided by 2, which would be KD over 2. So I exert a force in that direction, and I move at a distance D in that direction. So the work done to compress the spring is this force times the distance compressed, which is d. K d over 2 times d, which is 1/2 k d squared. Okay. This is also the energy, since I did this amount of work to compress the spring, this turns out to be the energy stored in the spring. This is energy stored in spring. And so if I just want to write that in terms of initial and final lengths, I could write that the potential energy or energy stored in this spring is 1/2 k x minus unstretched length squared. So I'll leave it at that and you guys can go. We'll do some examples next time. By the way, there's some subtleties here. That line the average force required. That means force proportional to stretch. That would give mass force proportional.
It's already compressed. So like on the problem, we were assuming that it was compressed. Meters.
Now tell me how much energy.
So like we had 1,000 meters.
I'll tell you how much energy. Yep. I'm gonna have to write a new test for you.
Sorry, bud.
Okay, I mean, I haven't heard it talk to anyone, so.
Yeah, well, I'm gonna have to, I mean, that's just what it is.
Did you get my email yesterday?
I did get your email yesterday.